Assalamu alaikum everyone, it's me Samia Singh from UMT Sialkot. I'm doing MS in chemistry and I'm in first semester, and today I'm presenting my presentation to Dr. Hammad, um, and our course title for the uh, uh, course is Chemical Industries, and my topic name is Nobel Prize in Chemistry in 2021. So the first one I will tell you about that what is a Nobel Prize. A Nobel Prize is one of a set of prizes that are awarded each year to people who have done important work in science, literature, or economics for world peace. The Nobel Prize is a celebration of excellence. The Nobel Prize is considered the most prestigious award in the world in its field. It is awarded to those who during the preceding year shall have confirmed the greatest benefit on mankind. Although he was a declared pacifist, many of Nobel's inventions helped make war more disgusting. It is believed that the Nobel Prize was an attempt by Nobel to leave a better legacy in the world than having improved military weaponry through his ingenuity. Now I have added Nobel Prize winners by year in chemistry. In 1901, Jabocus Henry Manhoff from Netherlands wins the Nobel Prize in the achievement of laws of chemical dynamics and osmotic pressure. So, this was the first person who won the Nobel Prize in chemistry. So now my topic is in 2021. So we will discuss about Nobel Prize in 2021. So the Royal Swedish Academy of Sciences has decided to award the Nobel Prize in Chemistry 2021 to Benjamin List and David Macmillan. Benjamin List was born 11 January in 1968. He is a German chemist who is one of the directors of Max Planck Institute for Coal Research and professor of organic chemistry at the University of Cologne. He co-developed organocatalysis, a method of accelerating chemical reactions and making them more efficient. He shared the 2021 Nobel Prize in Chemistry with David Macmillan for the development of asymmetric organocatalysis. Now, David Macmillan was born in 16 March 1968 in Belgium, United Kingdom. Of asymmetric organocatalysis. Chemists can create new molecules by linking together small or chemical building blocks but controlling invisible substances so they bond and in the desired way is difficult. Benjamin List and David Macmillan are awarded the Nobel Prize in Chemistry 2021 for the development of a new and indigenous tool for molecule building, organocatalysis. Its uses include research into new pharmaceuticals, and it has also helped make chemistry greener. Many industries and field of research depend on chemists' ability to build new and functional molecules. These could be anything from substances that capture light in solar cells or store energy in batteries to molecules that can make light weight running shoes or inhibit the progress of disease in the body. However, if we compare nature's ability to build chemical creations with our own, we were long stuck in the stone age. Evolution has produced incredible specific tools, enzymes for constructing the molecular complexes that give life its shape, color, and functions intentionally. When chemists isolated these chemical masterpieces, they just look at them in admiration. The hammers and chisels in their own toolboxes for molecular construction were blunt and unreliable, so they often ended up with lot of unwanted byproducts when they copied nature's product. So new tools. New tools for finer chemistry. Each new tool that chemists have added to their toolbox has increased the precision of their molecular construction. Slowly but surely, chemistry has progressed from chiseling in stone to something more like fine craftsmanship. This has been of great benefit to humanity, and several of these tools have been rewarded with the Nobel Prize in Chemistry. Many molecules exist in two variants when one is the mirror image of the other. These often have completely different effects in the body. For example, one version of the limonene molecule has lemon scent while its mirror image smells like orange. The discovery being awarded the Nobel Prize in Chemistry 2021 has taken molecular construction to an entirely new level. It has not only made chemistry greener but also made it much easier to produce asymmetric molecules. During chemical construction, a situation often arises in which two molecules can form which, just like our hands, are each other's mirror image. Chemists often just want one of these mirror images, particularly when producing pharmaceuticals, but it has been difficult to find efficient methods for doing this. The concept developed by Benjamin List and David Macmillan, asymmetric organocatalysis, is as simple as it is brilliant. The fact is that many people have ever wondered why we did not think of it earlier. So, catalysts accelerate chemical reactions. In the 19th century, when chemists began exploring the ways that different chemicals react with each other, they made some strange discoveries. For example, if they put silver in a beaker with hydrogen peroxide, the hydrogen peroxide suddenly began to break down into water and oxygen, but the silver which started the process did not seem affected by the reaction at all. Similarly, a substance obtained from splitting grains could break down starch into glucose. In 1835, the renowned Swedish chemist Jacob Oberilsted started to see a pattern in this in the Royal Swedish Academy of Sciences annual report describing the latest progress in physics and chemistry. He wrote about a new force that can generate chemical activity. He listed several examples in which just the presence of a substance started a chemical reaction, stating how this phenomenon appeared to be a considerably more common than was previously thought. He believed that the substance had a catalytic force and called the phenomenon itself catalysis. So, catalysts produce plastic, perfume, and flavor some food. A great deal of water has run through chemist pipettes since Brazil's time. They have discovered a multitude of catalysts. They can break down molecular or join them together. Thanks to these, they can now carve out the thousands of different substances we use in our everyday life, such as pharmaceuticals, plastic, perfumes, and food flavorings. The fact is, it is estimated that 35% of the world's total GDP in some way involves chemical catalysis. In principle, all catalysts discovered before the year 2000 belonged one of two groups that were either metal or enzymes. Metals are often excellent catalysts because they have a special ability to temporarily accommodate electrons or to provide them to other molecules during a chemical process. This helps loosen the bonds between the atom in a molecule, so bonds that are otherwise strong can be broken and new ones can form. However, one problem with some metal catalysts is that they are very sensitive to oxygen and water. So for these to work they need an environment free of oxygen and moisturizer. This is difficult to achieve in large-scale industries. Also, many metal catalysts are heavy metals, which can be harmful to the environment. Live catalysts work with astounding precision. The second form of catalyst is comprised of the proteins known as enzymes. All living things have thousands of different enzymes that drive the chemical reactions necessary for life. Many enzymes are specialists in asymmetric catalysis and in principle always from one mirror image out of the that are possible. They are also work side by side. When one enzymes finish with the reaction, other one takes other over. In this way, they can build complicated molecules with amazing precision, such as cholesterol, chlorophyll, or the toxin called strychnine, which is one of the most complex molecules we know of. We will return to this because enzymes are such efficient catalysts. Researchers in the 1990s tried to develop new enzyme variants to drive the chemical reactions for the bacteria. One research group working on this was based at the Scripps Research Institute in Carson, California, and was led by the late Carolus at Harvard State. Benjamin had a postdoctoral position in Harvard Research Program, the brilliant idea that led to one of the discoveries behind this pairs middle-class intellectual. It was all the history that is related how Benjamin and David Macmillan and see the like recognize like study all about previous research on their previous research on their topic. So when that they would have like full command on their topic. So Benjamin List thinks outside the box. Benjamin List work with catalytic antibodies. Normally, antibodies attached to organ varices or bacteria in our bodies, but the researchers at Scripps designed them so they could drive chemical reactions instead. During this work with catalytic antibodies, Benjamin List started to think about how enzymes actually work. They are usually huge molecules that are built from hundreds of amino acids. In addition to these amino acids, a significant proportion of enzymes also have metals that help drive chemical processes. But this is the point: many enzymes metals. Instead, the reactions are driven by one or a few individual amino acids and the enzyme. Benjamin List out of the box question was: do amino acids have to be part of an enzyme in order to catalyze a chemical reaction, or could a single amino acid or other or similar molecules do the same job? With the revolutionary and he got a revolutionary result. He knew that there was a research from the early 1970s where an amino acid called proline had been used as a catalyst, but that was more than 25 years ago. Surely, if proline really had been an effective catalyst, someone would have continued working on it. This is more or less, but Benjamin List thought. But Benjamin List thought he assumed that the reason why no one had continued studying the phenomena was that it had not worked particularly well. Without any real expectations, he tested whether proline could catalyze an aldol reaction in which carbon atoms from two different molecules are bonded together. It was a simple attempt that amazingly worked straight away. Like this one. Benjamin List stalk out his future with his experiments. Benjamin List not only demonstrated that proline is an effective catalyst, but also that amino acid can drive asymmetric catalysis, one of two possible mirror images. It was much more common for one of them to form than the other. Unlike the researchers, unlike the researchers, yeah. Unlike the researchers who had previously tested proline as a catalyst, Benjamin List understood the enormous potential it could have compared to both metals and environmentally friendly molecule. When he published his discovery in February 2000, List described asymmetric catalyst with organic molecule as a new concept with many opportunities, and designed the screening of these catalysts is one of the future aims. However, he was not alone in this. In a laboratory further north in California, David Macmillan was also working towards the same goals. Now we will discuss about the David Macmillan and discovery and his contribution in Nobel Prize in 2021. David Macmillan leaves sensitive metals behind. 2 years previously, David Macmillan had proved from Harvard to UC Berkeley. At Harvard, he had worked on improving asymmetric catalysis using metals. This was an area which was attracting a lot of attention from researchers, but David Macmillan noted how the catalysts that were developed were rarely used in industry. He started to think about why and assumed that the sensitive metals were quite simply too difficult and expensive to use, achieving the oxygen-free and moisture-free conditions demanded by some metals. Catalyst is relatively simple in a laboratory, but conducting large-scale industrial manufacturing in such condition is complicated. His conclusion was that if the chemical tools he was developing were to be useful, he needed a rethink. So when he moved to Berkeley, he left the metals behind and develops a simpler form of catalyst. Instead of David Macmillan started to design simple organic molecules, which was just like metals, could temporarily provide or accumulate electrons. Here we need to define what organic molecules are. In brief, these are the molecules that build all living things that have stable framework of carbon atoms. Active chemical groups are attached to this carbon framework, and they often contain oxygen, nitrogen, sulfur, or phosphorus. Organic molecules thus consist of simple and common elements, but depending on how they are put together, they can make complex properties. David Macmillan's knowledge of chemistry told him that for an organic molecule to catalyze the reaction he was interested in, it needed to be able to form a minimum ion. This contains a nitrogen atom which has an inherent affinity for electrons. He selected several organic molecules with the right properties and then tested their ability to drive a diel-aldo reaction, which chemists use to build ring of carbon atoms. Just as he had hoped and believed, it worked brilliantly. Some of the organic molecules were also excellent at asymmetric catalysis of two possible mirror images. One of them compromised more than 90% of the product. David Macmillan coins the term organocatalysis. When David Macmillan was ready to publish his result, he realized that the concept of catalysis he had discovered needed a name. Despite that researchers had previously succeeded in catalyzing chemical reactions using small organic molecules, but these were isolated examples and no one had realized that the method could be generalized. David Macmillan wanted to find a term to describe the method so other researchers would understand there were more organic catalyst to discover. His choice was organocatalysis. In January 2000, just before Benjamin List published his discovery, David Macmillan submitted his manuscript for publication in a scientific journal. The introduction states, "Herein we introduce a new strategy of organocatalysis that we accept will be amenable to a range of asymmetric transformations. The use of organocatalysis has boomed independently of each other. Benjamin List and David Macmillan has discovered an entirely new concept for catalyzing in 2000. In this area can almost be linked to a gold rush in which Neft and Macmillan leading positions that have designed multitudes of cheap and stable organocatalysis, which can be used to drive a huge variety of chemical reactions. That's why they were they were uh, they were they have that's why they win the Nobel Prize in 2021. Not only do organocatalysis often consist of simple molecules in some cases, such like nature's enzyme that can work on conveyor belt. Previously, in chemical production processes, it was necessary to isolate and purify each intermediate product. Otherwise, the volume of byproducts would be too great. This led to some of the substances being lost at very step of a chemical construction. Organocatalysis are much more forgiving, as relatively often several steps in a production process can be performed in a broken sequence. This is called a cascade reaction, which can considerably reduce waste in chemical manufacturing. Strychnine synthesis is now 7,000 times more efficient. One example of how organocatalysis has led to more efficient molecular construction is the synthesis of the natural and acadically complex strychnine molecule. Many people will recognize strychnine from books by Agatha Christie, Queen of the Murder Mystery. However, for chemists, strychnine is like a Rubik's Cube, a challenge that you want to solve in as few steps as possible. When strychnine was first synthesized in 1952, it required 29 different chemical reactions and only 0.009% of the initial material formed strychnine. The rest was wasted. In 2011, researchers were able to use organocatalysis and a cascade reaction to build strychnine in just 12 steps, and the production process was 12,000 times more efficient. Organocatalysis is most important in pharmaceutical production. Had a significant impact on pharmaceutical research, which frequently requires asymmetric catalysis. Until chemists could conduct asymmetric catalysis, many pharmaceuticals contained both mirror images of a molecule. One of them was active while the other could sometimes have unwanted effects. A catastrophic example of this was the thalidomide scandal in 1960s, in which one mirror image of the thalidomide pharmaceutical caused serious deformities in thousands of developing human embryos. Using organocatalysis, researchers can now make large volume of different asymmetric molecules relatively simple. For example, they can artificially produce potentially creative substances that can otherwise only be isolated in small amounts for rare plants or deep sea organisms. A pharmaceutical companies, the method is useful to streamline the production of existing pharmaceuticals. Example of this include proxenetine, which is used to treat anxiety and depression, and the initial medication ostromen, which is used to treat respiratory infections. Some ideas are often the most difficult to imagine. It is possible to list thousands of examples of how organocatalysis is used, but why did no come up with this simple, green and cheap concept of asymmetric catalysis earlier? This question has many answers. One is the simple ideas are more often most difficult to imagine. Overview is obscured by strong preconceptions that about how the world should work, such as the idea that the only metals enzymes can drive chemical reaction. Benjamin List and David Macmillan succeed in seeing past these prescriptions to find an intricate solution to a problem with which chemists had struggled for decades. Organocatalysts are thus bringing right now the greatest benefit to mankind. So that's all from my side. The next slide is about references. Thank you so much.